In 1800, the double-slit experiment performed by Thomas Young provided evidence that light is a wave. Around 1860, Maxwell came up with his theory of electromagnetic waves, and physicists agreed with this theory, and it was believed that light displays behaviors of a classical wave. However, in the 1880s, this idea was contradicted due to studies conducted of what happens when light is shown onto metal. The electrons of metals are free to move around within the metal, but they are still bounded to the metal because of the attraction between the electrons and the positive charges of the nuclei of the metal atoms. In order to remove the electrons from the atoms, energy is required. The work function, symbolized by an uppercase W, is the minimum energy needed to remove an electron bound to a metal surface. It is usually measured in electron volts, written eV. 1 electron volt is equal to 1.6 times 10 to the negative 19 joules, and 1 electron volt is the amount of energy given to an electron that accelerates through a potential difference of 1 volt. The work function of a metal is measured by applying an electric potential. In this setup, if the electric potential energy of the electrons is greater than the work function, the electrons are ejected from the top metal to the metal plate. In other words, electrons will jump across the vacuum gap from the metal sample to the metal plate when the voltage applied is greater than a certain value. The equation for work is W equals E delta V, where delta V is the smallest electric potential difference where electrons begin to be ejected, and E is the elementary charge, 1.6 times 10 to the negative 19 coulombs. Note that the work function is different for different materials. The photoelectric effect is defined as the phenomenon of electrons being ejected from a material when exposed to electromagnetic radiation. When light strikes a metal surface, the electrons of the metal absorb the light. If the absorbed light energy is above the metal's work function, the electron is ejected from the metal. Around 1900, experiments conducted studying the photoelectric effect showed that the light's frequency must be greater than the threshold frequency in order for the electrons to be ejected. The threshold frequency, F subscript O, is the minimum frequency at which electrons are ejected from a material. The experiments also revealed that the kinetic energy of the ejected electrons vary linearly with light frequency. These results could not be explained by the classical wave theory of light, and a new theory of light was required. In 1905, Einstein's quantum theory of light was proposed, and it was able to explain the photoelectric effect. Einstein introduced light as a collection of particles which we now call photons. A photon is a discrete bundle of energy carried by light. They do not have any mass and they exhibit interference effects. For these two reasons, they are unlike the particles described by classical physics. Each photon carries a parcel of maximum kinetic energy that is given by the equation E subscript photon equals hf, where f is the frequency of light and h is Planck's constant with the value of 6.63 times 10 to the negative 34 joules second. This quantum theory explains the two problems that arise when trying to explain the photoelectric effect with classical theory. First, the experiments of the photoelectric effect showed that the threshold frequency is not related to the intensity of light in any way. This contradicted the classical wave theory, which predicted that the energy carried by a light wave is proportional to the intensity of that light. This meant that electrons should be ejected by increasing the intensity of light to a high value. However, the experiments conducted showed that no electrons are ejected when the frequency of the light is below the threshold frequency, regardless of light intensity. Quantum theory explains that the absorption of light by an electron is very similar to a collision between a photon and an electron. The energy carried by the photon, hf, is absorbed by the electron, and if it is less than the work function, the electron cannot leave the material. When light intensity is increased for monochromatic light, the number of photons arriving each second increase, not the energy of a single photon. However, the energy of each photon depends on the frequency of the light. Therefore, the frequency of the light must be greater than the threshold frequency in order for electrons to be ejected. Second, the experiments showed that the kinetic energy of an ejected electron is independent of the light intensity. According to classical theory, the kinetic energy is directly proportional to the intensity of light, so increasing one should also increase the other. But the results of the experiment showed that the kinetic energy of ejected electrons depends on the frequency of the light, not the intensity. Using the equation E photon equals hf, if we replace f with the threshold frequency in the photoelectric effect, the energy of the photon is equal to the work function, W. This ejected electron has no kinetic energy since the photon in this case would have just enough energy to simply eject the electron from the metal. In the case a photon has a higher frequency, the excess energy would become the kinetic energy of the electron, so Ek equals hf minus h threshold frequency, and Ek equals hf minus W. This is the equation of a straight line, so Ek is linearly proportional to f. The value of h is the slope of this line, and when calculated by the photoelectric effect, the value agrees with Planck's constant.
We learned that Einstein's quantum theory states that light energy can only be absorbed or emitted as single photons. The classic theory of electromagnetic waves gives us the formula P photon equals hf over c. In this case, P is the momentum, h is Planck's constant, and c is the velocity at which light travels in a vacuum. In Einstein's case, he derived the formula for the relativistic energy and momentum for an object with zero mass. This is how he derived the formula. But how do we know that photon momentum really exists? Well, in 1923, American physicist A.H. Compton discovered evidence of the momentum carried by the individual photons. His experiment involved a directed beam of high-energy X-ray photons at a thin metal foil. This is what happened in the experiment. The foil ejected both electrons and lower-energy X-ray photons. This created the Compton effect, the elastic scattering of protons by high-energy photons. Compton's experiments were different than other photoelectric experiments in the sense that he used different metals and different beams with higher energy photons. When a photon comes into contact with matter, an interaction takes place. These are the 5 main interactions that may occur. Number 1. A photon may simply reflect, as when photons of visible light undergo perfectly elastic collisions with a mirror. Number 2. A photon may free an electron and may be absorbed in the process, as in the photoelectric effect. Number 3. A photon may emerge with less energy and momentum after freeing an electron. After this interaction with this matter, the photon still travels at the speed of light but with less energy and lower frequency. Number 4. A photon may be absorbed by an individual atom and elevate an electron to a higher energy level within an atom. The electron remains within the atom, but it is in what is called an excited state. Lastly, a photon can undergo pair creation, where it becomes converted into 2 particles with mass. In 1901, Max Planck was studying black bodies and black body radiation. Firstly, what is black body? A black body is an object that absorbs all radiation reaching it. Black body radiation is the radiation emitted by an ideal black body. The specific problem that puzzled Planck is represented by a glowing oven. For example, a regular pizza oven. At that time, physicists knew that the electromagnetic waves formed standing waves as they reflected back and forth inside an oven. These standing waves are just like the standing waves on a string. Standing waves on a string have frequencies that follow the pattern Fn equals NFO, where Fo is the fundamental frequency and N equals 1, 2, 3, etc. the spectrum of blackbody radiation by hypothesizing that the energy in a black body comes in discrete parcels called quanta. Planck showed that his hypothesis supports the theory of blackbody radiation so that it correctly produces the blackbody spectrum. The wavelength at which the radiation intensity of a black body is the largest is denoted by lambda max and is determined by the temperature T of the black body through the expression called Wien's law. The formula for this is lambda max equals 2.90 times 10 to the power of negative 3 meters per Kelvin over T. T is measured in the Kelvin temperature scale. According to Wien's law, the value of lambda max and hence the color of the black body depends on the temperature. A hotter object has a smaller value of lambda max, and the entire black body curve shifts to shorter wavelengths when the temperature is increased. A flame that appears blue is therefore harder than one that is red. Consider a double slit experiment performed with light with a very low intensity. Suppose a screen responds to the arrival of individual photons by emitting light from the spot where the photon strikes. The result would then appear as it does in this diagram. The photoelectric effect and blackbody radiation demonstrate that photons exhibit both wave-like and particle-like properties.